Think forward. Think Research Channel.
Well, you know, seeing is believing, right? And the Center for Visualization is really aimed at giving us a new way of seeing, a new way of interpreting what we see, of thinking about what we see, and that's critically important. New ways of seeing have driven science in the past, and I think new ways of seeing will help us drive new science and new ways of thinking about our world.
These are just features you just don't see in, you know, your typical construction.
Our building would be the first residential project certified in the state of Kentucky and one of the first in the nation.
It's always striking when people first come in and they're like, wow. And it's that way for us. We've been here several months and it's still very striking to live in the house.
The residence house is a proof of concept design with an affiliation agreement with Design Lab, which is a private not-for-profit located in Kentucky, whose sole purpose is to enhance the built environment through research and education. Their affiliation with the University of Kentucky and the College of Design enabled the residence house, which is a LEED certified house, single family, that was market driven, that's also located in a historic neighborhood.
We were having breakfast downtown, and we thought if we walked around, it might jostle something loose. And we're quite taken with it. We really wanted to get a house that had contemporary design.
The idea of doing the residence house and actually naming it the residence house as an experimental house was really meant to create a resonance between the historic fabric where the building is located and the contemporary design itself.
We just sort of came upon the place, and that's how we kind of met up with Greg and the whole design lab project and the student design project, which we really liked that idea right from the get-go.
My research into flexible form manufacturing really situates itself between a seam between building information modeling and digital fabrication. Sometimes that seam is thin, where you can directly export your drawings and information directly from the model into digital fabrication. Our school, however, has prided itself on hand making. So how do you take the digital concepts and merge them synthetically with the process of digital fabrication and hand making? And the residence house actually was able to do that as well. We took it on from another concept, from an historical standpoint, where there's an historic neighborhood. The West End suburb was an area that was ripe for infill development. They were looking for a new model that would actually create a resonance and change the way that developers would build in that neighborhood.
Our
architecture is a complex profession in terms of how you have to convert something that you're drawing two-dimensionally or making a model of into a full-scale form with materials that have weight and have properties that you can't mimic in models or drawings.
We built and designed everything digitally, so we were able to modulate the entire building and come up with a schema that would allow for an ease of manufacturing to take place.
Digital fabrication is essentially working with a modeling environment inside the computer where you enter in all of the data that you're going to use to design and develop a project, and then that data is also used to fabricate the final pieces.
We use a process here called building information modeling, and building information modeling is essentially a drawing data structure that allows for three-dimensional design and two-dimensional data to be seamlessly integrated with one another.
The capacity to model and to look at space in a much more complex way. I mean, it's because it's a three-dimensional design, you have to be able to understand it in implications behind you as important as in front of you. Understanding it from a 2D representation to a 3D actuality is difficult for most people to understand. The new programs have allowed people to put it in front of themselves quicker to see the product.
It also allows you to extract information from the project that would get into the framing of the building, into the roofing, the materials, and dynamically understand from a costing standpoint that the quantities that are being used for the design process. So if we changed out a siding, say from redwood siding to copper, it would be very easy to track those changes throughout the building because of the way that we modeled it. We went from that seamless integration of 2D to 3D and the ability to control that as a data structure into the fabrication process, where things that we knew that we wanted to be able to control, like the redwood siding or the flooring or even the copper skins, could easily be panelized after the three-dimensional model was made.
You look at what you have and you say that's not right, or these parameters need to change, and you take that information and you feed it back into the beginning and then you redo it again, and you can test it in multiple ways from conception all the way through physical form. The computer is driving the process using digital fabrication.
That level of abstraction then allowed for individual students to extract data from that model and then concentrate and focus on an aspect of the building, whether that be the cabinetry, the flooring, the intersections of details, the locations of windows. And then we work dynamically from that building information model through a digital fabrication point to set up data structures to control and run machines, whether or not it was CNC milled or using profile machines at the Wood Utilization Center. We were able to custom fabricate every aspect of the building. A profiling machine is essentially, if you liken it to making keys, first thing you have to do is you have to make a blade that has the exact profile of the end piece, say a piece of cornice work or the thickness of a flooring. You make the keys and you put it into a profiling machine that spins rapidly. Again, that's computer numerically controlled using Mastercam or some type of G-code. That G-code then allows the machine to operate, and it tells you the pace that you want it to operate at, and the blades that you've already digitally manufactured allow for any standard stock, like a 2x4, to run through this machine, and it creates profiles along its edges. We panelized the entire building, which would have been the most efficient way of framing it. The first panel took 1 day to make and to learn how to use the tools. The other 74 panels of the house took 2 days to do. The entire framing of the house was done within a week. So the idea then was to take that expediency and then to start to experiment with materials and see where we could limit waste, because everything was digitally made and digitally designed. So we knew how to cut, precisely to cut, and what was going to be lost, and that loss was then incorporated back into the building.
They were able to take, basically trees and convert them into the product and see the amount of waste that was generated.
U.S. Green Building Council started a Lead for Homes pilot program in 2005. I submitted the project to the U.S. Green Building Council and was selected by our region as one of the homes for the Lead for Homes pilot program. Our building will certify at the gold level. You have certified, you have silver, gold, and platinum. Right now in Kentucky, there's one LEED certified building, and it's at the LEED certified status of silver. Our building would be the first residential project certified in the state of Kentucky and one of the first in the nation. Our building was specifically came in at the gold level because of the innovations and the building technology that we had incorporated into it. We used standardized materials but integrated them in non-standard ways.
A lot of the stuff in here is very custom. It's very, I mean, it really is, you can tell, it really is a concept house. I like the natural light. There's lots of natural light in the house.
What we created was a two-story living room space that allows natural sunlight to filter in during the day. The living room, which opens up mostly to the south-facing orientation, allows for sunlight to come in during the winter, but we designed sunscreens that were specifically calibrated to block out the direct heat gain from the sun during the summer months. So between March and October, you block out the light, but between October and March, you allow the sunlight to come in.
The floor in the great room here, if it's a sunny day and it's 40 degrees outside, without any real assistance from the HVAC, it can get close to 70 degrees in here, just from it soaking up if we open up all the shades and let the sun come in, it'll soak that up, and really the heat won't kick on until the evening.
We also use some materials on the inside that won design awards in Italy for being able to absorb the sun's light during the day and then let it naturally dissipate over the course of the night. That allows us to not have to turn on air conditioners or heating during the day, and then it also helps to supplement the heat during the night.
Our last house was half this size, and our probably total energy costs the last 2 months were, I would say, about at least 30 to 40% lower.
From a green standpoint, one of the biggest issues that we faced was a lot of products that are very readily available are not necessarily green. They're not manufactured in a way that would make themselves sustainable to the environment. So not just getting materials that were green in context, but also in the way that they were manufactured.
One of the opportunities that this project afforded us was to use materials from as close of a source as you could find it in a raw state.
So there was an enormous amount of research that was done by the students, which was another way that they were seamlessly integrated into the project, was to find materials that are healthy throughout the entire process of their being. A lot of that was forest certified lumber that we used. That was green in the way that it's manufactured. We were able to use materials that would naturally patina and seal themselves, so they would never have to be coated or recoated or repainted. So the redwood siding, the copper siding would naturally patina.
I love the exterior of the house. I love the copper shingling. I love the redwood siding and the different. It's not flat. That's one of the things I like about the house. Again, there's lots of depth. There's lots of dimensions to it.
Because of the southern exposure that we were oriented at, we did not want the heat gain to go directly into the building. So we created these shadow screens on the outside to create shade on the building, therefore cooling the building. We used recycled material as much as we could. We used the digital fabrication methodologies to limit waste. And in fact, if you were to think about the biggest green thing that we could have done for the project was probably in two ways. One, the compact fluorescent lighting that we used, so therefore we wouldn't have to change light bulbs a lot. For the height lighting, for the ceiling lights for the building, we used LED lights that would last for 10,000 hours, so you wouldn't have to change light bulbs very often. But the biggest thing that we did is through the digital fabrication process, we were able to incorporate the idea of loss into the design process. So therefore, we could minimize waste, and any cut scrap that we had would be immediately integrated back into the building. For instance, with the flooring, we work with the Department of Forestry to source trees. We use portable milling machines to chop down the trees, cut them into planks, and made our own flooring from that. That process allowed us to get a yield of 2 or 3 panels of flooring per board. The scraps of that process were then put off on the side and then later butcher blocked back together to make a solid oak staircase that now is a figural element inside the house. So that idea of using material to its most efficient standpoint and then reincorporating it was fundamental to our design process.
In terms of the actual construction, I know some of the materials they used were recyclable, like the copper on the exterior of the house. They recycled everything that was left over. And there was a lot less waste with the house, and I think that's because they did a lot of the cutting and designing on site and try to reuse things. The floors, they reused pieces of the floors, and I think in building the stairs, and a number of things like that.
A typical construction project of our size would generate about 18 tons of waste that would go into a landfill. We were able to limit that to just above 3 tons of waste. So that, as a green mentality, was huge. One of the major aspects that we did for the project was a process called rainwater harvesting. All the water that comes off of the roof during a rainstorm actually gets collected in a below surface trough and goes into a sump pump system that gets pumped back out to the vegetation that we have in the front. All the vegetation that we have on the property is drought tolerant and is native to Kentucky. So in one way, we're taking things that are naturally coming free to us anyway, like water and sun, and being able to bring that back to the project. One of the biggest savings that we have in the house is the way that we built it as a system. So if you start from the outside system, heat does not go into the building because of the way that we set up the rain screen idea with the ventilation. So any moisture that comes into from the exterior of the facade, or would typically build up because of heat gain, naturally weeps out through the bottom. Any of the heat that gets into the building ventilates out through the top. One of the aspects of that green systems approach is in the insulation.
In terms of comfort-wise in the house, being so well insulated, you get a lot less variation in temperature.
A typical batt insulation, the pink stuff, as you would know it, doesn't conduct very well in terms of different types of thermal expansions. What we ended up using was a cellulose material because that was readily available in Kentucky at the time. Now, the projects that we're using now, like Icynene and spray foam insulations, actually act as an air barrier as well as a moisture barrier. So you won't have that type of exchange between the inside and the outside of the space.
Everything is very well sealed, very high quality windows. They're installed very well. And that's going to cut down on the amount of basically air seepage that you get coming in and out of the house.
With the windows, we used low U factor windows, which are very high energy performing. We used low E windows that would reflect away any heat gain that would come in through the windows. Allowing air to move dynamically through the space, we set up what we called the light vortex, was in one case set up to create a light rendition, a continuous light rendition over the course of the day using natural light coming in from the outside. But it also allowed us to create a vortex-like shape where air would come up against the windows and use the vortex to wrap air back in and recirculate it back into the house. So as a system, you start to get very dynamic in the way that air moves through the space. So there's really no heat pockets within the house as you traditionally have in tall roof systems. A typical high-performance house would have about 0.35 air changes per hour. Our house has 0.11, which is amazingly high performing. One of the amazing aspects of the residence house is that it was built and designed by myself and by my students.
The student involvement in the project was eye-opening to them.
The architecture program tends to be it's less structural than most classes and not quite as a rigid timetable. So I think it makes it slightly easier going from a non-structured environment in the classroom to a slightly non-structured environment in the workforce. It kind of prepares you better and you know what you have to do.
We get to design a lot of the house and work on parts of the house that most design studios don't get to work on, like the HVAC, finding different materials that we're actually going to use, doing cost analysis of what we're going to build, and then when we actually get to build, we'll be able to apply the knowledge that we've been spending all this time on.
It's been really good real-world experience, and I think it'll be quite applicable once we get out.
We already know building information modeling, and we know how to do digital fabrication, but they've never been integrated to design at the scale of an inhabitation or a house. So the students then took that ability to seamlessly integrate the building information modeling and the digital fabrication to apply to this house. And it went from 15 individual schemes to one collective scheme. And then once we had the collective scheme, we then extracted the data structures to create the framing plans and then to create all the custom cabinetry, the siding, and the flooring. So the students were involved throughout that entire pre-design, design, fabrication, and then the framing of the house, the tilt-up framing of the house, the cladding, the construction and installation of the staircase, and through all details aspects of it. We had initially 15 students involved in the studio. That the idea was initially to build within this historic neighborhood using this digital-to-digital process and this art-to-part framing to do it in one semester. What became problematic is the necessity to almost design everything. We designed the siding, the copper skins, we designed the redwood siding, we designed the flooring, the custom cabinetry inside the house, and then almost you ask yourself, what do we not do? One of the unique processes that we were able to do with the digital-to-digital process is actually bring the classroom out of the classroom and bring it down to the construction site.
I first got involved in the project when I was a student at the University of Kentucky School of Architecture. I was the framer, basically. I've worked some jobs before, kind of just as doing grunt labor and then kind of stepping up. This job was not like that. In a way, it was a way for me to apply this knowledge that I got from this job, being a fairly large-scale residential project. Now I can apply each of those steps that I now have a little experience in to bigger jobs.
It was really interesting, and it was one of the first times that I had ever been on a construction site where a computer was as useful as a hammer on a construction site. Students would work side by side with laptops, pulling up details that they would be using. We had drawing sets that were being used by all contractors on the site, but it was also very instrumental for the students to draw what they did that day, or if they came up with a detail where they had to resolve something almost through improvisation, they could immediately then integrate that back into the model. So the comprehensive model that was done at the end of the project or during the entire construction process was uniquely different than the building model that we started off with that was actually done inside of the classroom setting. So part of the idea was to bring the classroom with the students and then to get the students out of the classroom.
The whole concept of a real-world project versus something that's just academically based. It's something that is transformative for the student in their experience.
I think one of the things that's really interesting for the students is that you get them out working with people that are actually doing things for the building industry.
It was really a dynamic intersection between the students at the University of Kentucky that were made up of students in architecture, engineering, interior design, and historic preservation that collaboratively worked together in order to build the house. And one thing I should also note about the residence house is that even though it was built in 3 semesters, it was still built in 1 calendar year, which at that scale, with the level of complexity that we had and the enormous amount of custom fabrication throughout the entire project, a typical house of that size, that quality, and that custom nature would actually take 2 to 3 years to do. So utilizing students that were wholly entrenched to the project was an amazing aspect of it. Habitat for Humanity approached Design Lab and my studio in the summer of 2006 to design an affordable housing strategy for a rehabilitation project, which is historic in nature. Reestablishing the historic nature of the building, but doing it through the lens of green building and high performance, also under the lens of low maintenance, is something that we're in the process of designing right now. We're incorporating performance-based modeling into our design. The idea is actually to try to design a net zero constructed house, where instead of using high levels of electricity, we're actually net metering and incorporating electricity that's given to us from the sun and selling that back to the local utility. Now we're at a point in this semester where we're waiting for Habitat to involve a family with us, so that the way the students would actually get to know the families and understand more seamlessly what the relationship of a person in that context would be and what needs that they have specifically, so we can design towards those needs. I had a professor at Virginia Tech, Olivio Ferrari, who always challenged us to say, what's next? And it's mind-boggling to see that the materials that we build with are still the materials that the Romans built with and the Egyptians built with. They're still several thousand years old. And what I'm really interested in doing is finding new materials, new processes that could be applied to construction that are sustainable, not only in the way that they would sustain themselves on the environment, but also in the way that they're made, manufactured, installed, and then their own life cycle costing. The idea of taking these projects from installations to inhabitation, from an art to part concept, is really a crucial element of my research.
Well, you know, seeing is believing, right? And the Center for Visualization is really aimed at giving us a new way of seeing, a new way of interpreting what we see, of thinking about what we see, and that's critically important. New ways of seeing have driven science in the past, and I think new ways of seeing will help us drive new science and new ways of thinking about our world.